Okay, so on page 1, this first problem gave you a rule, right? 1 less than twice the previous number, 2n minus 1, where this is going to be our previous term. So let's say we start with 5. You could start with whatever number you want, but let's say you start with 5. That means our next number is going to be 2 times 5 minus 1. That would be 10 minus 1, that's 9. And then I follow the same rule to find the next number. So that would be 2 times 9 minus 1. That would be 18 minus 1 is 17. And then 2 times 17 minus 1. And I would continue that pattern on and on until I, well, in this case, got to that last blank spot on my paper, but I would continue that pattern using that same rule. That makes sense? Okay. For the rest of the ones that you looked at, or for the next couple at least, they didn't give you the rule. You had to figure it out. So for problem number 2, it says these are all flowers. So we've got some shape, some figure made out of flowers here, and it wants to know how many flowers will be in the next few pictures that we're showing them. Well, if I look at my first picture, I've got 1, 2, 3, 4, 5, 6, 7, 8. And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is there a pattern here that we could take advantage of? What are we doing? We add 4 each time, right? I get 1 more flower on each side of my square. So we add 4 each time. So I don't have to draw out the next picture to know how many flowers there will be. I could just add 4 to that last term. So I know the next picture should have 20, and then the next one should have 24, and then the one after that should have 28. How about this third problem down here towards the bottom of page 1? We start off with 2, and then we've got 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I take a look at my pictures, it looks like I add 1 to the end, add 1 to this guy, and then add 2 to that sort of middle term. Then if I move the next step over, I added 1 more to this column. I added another column here. I added 1 on top and made this new column the same height, and then I've still got that 1 at the end. So the next one I would expect to probably add another block here, add another block here, and a whole nother new column all the way down, with this guy kind of scooted out. So I could count up how many blocks that would be. But if I take a look at the numbers that I've got here, maybe I can pick that pattern out of here. So how would I get from 2 to 6? I could add 4. How about to get from 6 to 12? Add 6. So what do you think I would add for the next one? 8. So I would get 20. And then what would I add? 10. So I'm not adding the same thing every time, but there is a pattern to what I'm adding here. This would be 30. And then if I add 12, continuing that pattern, I would have 42. So these are all examples of sequences. There's some sort of pattern here. There's some sort of rhyme or reason that connects, some sort of rule that connects these terms, and I can use that same rule to find terms moving forward. Okay, so that's the idea behind a sequence. Today, we're going to focus on one particular type of sequence. So if you turn the page to page 3, we've got a couple sequences here at the top of page 3 that I want to take a look at to sort of introduce one specific type of sequence that we're going to focus on. Okay. So again, the big idea for a sequence is that I have a rule that I can use every single time to get to the next term. Okay. So how could I get from 40 to 120? Multiply by 3. Will multiplying by 3 take me from 120 to 360? Yeah, will it work for every single one of these terms? I can always multiply by 3. So what would be the next term? 9,720 if you multiply by 3. Take a minute and work on these next 3 sequences. What am I doing in this second sequence? Multiply by 4. To get from 2 to 8, I multiply by 4. To get from 8 to 32, I will multiply by 4. So what's the next term in our sequence? 2,048. Good. How about this third sequence here? We're dividing by 2. That would be the same as multiplying by a half or 0.5. So we're cutting our number in half every time. 62.5 times a half would give us what? Perfect, 31.25. And then how about this last one? This one was probably the hardest one here, the last sequence. Anybody get that one? Okay, so this one is tricky. So first I want you to notice our numbers are getting smaller. I'm not subtracting the same amount every time. And there's not a pattern to what I'm subtracting. So I must be multiplying by something. To multiply and get a smaller number means I have to be multiplying by something less than 1, like our 1/2 up here. If I multiply by something bigger than 1, these numbers would get bigger. Not 1/8. Here's where I'm sort of losing a fourth of it every time. Yeah. So that means essentially I'm keeping the rest of it, and that's what we want to figure out. Here's another way that you could get that number. What do I multiply by? If it's ever unclear, take your calculator, take that second term, and divide by the first term. So you said it looks like it's reducing by a quarter each time? Yep, we're multiplying by 0.75 or 3/4. Now, I'm going to check this just to make sure. So this should work for every single pair of terms in my sequence. So let's take 144 and multiply by 0.75. Is that the next term in my sequence? Yep. So what we're multiplying by here is 0.75. So my last term would be 81 times 0.75, which would give us 60.75. So notice for each of these sequences, we're multiplying by something to get the next term every time, okay? So we looked at sequences where we were adding the same thing, or we added, but we changed what we added, but there was a pattern to how we changed it. Here, we're multiplying by something every time to get the next term. So let's look at another example. It's a little bit different context. So I'm going to take a piece of paper and cut it in half. So I've got my piece of paper, I cut it in half, and then I'm going to take those halves and stack them on top of one another and cut the stack in half. And I'm going to keep doing that. So what we're going to keep track of are how many pieces of paper we have and the area of each piece. So we're starting with a piece of paper that's 8 inches by 10 inches. Before I make any cuts, how many pieces of paper do I have? 1. Yep, our whole big sheet of paper. And since our paper is 8 inches by 10 inches, that means its area would be 80 square inches. Now I've got my whole big piece of paper and I cut it in half. How many pieces do I have now? 2. And since I cut it in half, that means one side of my sheet of paper has to be half of what it currently is. Does that make sense? I'm going to choose to cut the longer side in half, but it doesn't matter which side you pick. So I'm going to say that my paper is now 8 by 5. If I cut the other side and it were 4 by 10, I would end up with the same area. So it doesn't matter which side I cut. And now I'm going to take those 2 pieces of paper, stack them on top of one another, and again, cut in half. So how many pieces would I have now? 4. And again, I've cut a side in half. I'm going to choose to cut the even length side in half just to make our numbers a little nicer. So this would be 4 times 5, giving us an area of 20 square inches. And then I stack up these 4 pieces of paper and I cut them again. So how many pieces would I have now? 8. And again, I'm going to cut the even side in half. So that would be 2 times 5 for my area. If I take my 8 pieces and cut them in half, how many would I have? 16. And again, I would have to cut a side in half. So 1 times 5 gives me 5 square inches. Then I'll do this one more time. Let's take our 16 pieces, cut them all in half. So now we've got 32 pieces, and they're each 1 by 2.5. So their area would be 2.5 square inches. I would like you now to take a look at the relationship that we've got for each of these different sort of categories of things that we kept track of. So I'd like you to make a scatter plot for me based on number of cuts versus the number of pieces of paper we ended up with, and then number of cuts versus the area of each piece. Okay. Quick scatter plot for each of those for me. So your scatter plot should look something like this. Do these look like linear relationships? Could I draw a straight line through all those points? No. So what we have here are, again, some what we're going to call in just a second geometric sequences. Because what's the pattern here? How do I get from 1 to 2? Or from, let's say 2 to 4. What can I do to get from 2 to 4? Multiply by 2. Does that work to get me from 1 to 2? Multiply by 2? Yeah. From 4 to 8, multiply by 2. And then how about from 80 to 40? Divide by 2 or multiply by a half. From 40 to 20, could I do the same thing? Yeah, multiply by a half. So this relationship that we're seeing here, where I multiply by something to get that next term in my sequence, not going to be linear. We won't look at sequences that can be described by a linear relationship, but these guys are what we call geometric sequences. So on the next page, a geometric sequence is a sequence where to get the next term, I have to multiply the previous term by something, and I'm always multiplying by the same number. Okay. So if I have the sequence 2, 6, 18, to get from 2 to 6, I multiply by 3. To get from 6 to 18, I multiply by 3. So to get from 18 to that next number, I would multiply by 3 and get 54. When I've got 54, I can get the next term by again multiplying by 3. So I multiply by the same thing every time. That's what we call a geometric sequence. If I multiply by the same number every time. That number that we multiply by is called a growth factor or a common ratio. In Algebra 2, when we talk about exponential functions, we'll use this term growth factor a lot. Growth factor or common ratio, they mean the same thing. And we're looking at what is it that I multiply to get to the next term. So we've got a chunk of sequences here that we actually saw on the top of the last page. And I want to know this time, what's the growth factor? So how did we get from 40 to 120? We multiplied by 3. So 3 is our growth factor. How did we get from 2 to 8? We multiplied by 4, so our growth factor is 4. To get from 1,000 to 500, we multiplied by a half, or if you'd rather, 0.5 means the same thing, so that's our growth factor. The 256 to 192 to 144, remember this was 0.75 for our growth factor, or 3/4 if you'd rather. And then what about our number of pieces? So if I flip back to the last page, I multiplied by 2. And how about our area? Yeah, we cut this in half each time. We multiplied by a half. Or again, 0.5 is the same thing. So I need to figure out that growth factor anyway, to figure out how to find that next term in the sequence. As soon as I know what I'm multiplying by, I've identified my growth factor. Let's take a look at another example here. We're going to identify the growth factor, which again, we have to do anyway to figure out the next term in the sequence. And then we'll use that growth factor to find some missing terms in our sequence. So for our first sequence, we're starting with 1.5. If you are not comfortable with the first term in the sequence, move to the second term. You have to be doing the same thing each time. So it doesn't matter if I look at terms 1 and 2 or terms 2 and 3. So how would I get from 3 to 6? What would I multiply by? 2. I'm multiplying by 2. That means my growth factor is 2, and I'm always multiplying by 2. So 6 times 2 would give me 12. 12 times 2 gives me 24. 24 times 2 gives me 48. How about B? What's our growth factor for B? 3. So 360 times 3 would give me 1080. And 1080 times 3 gives me 3240. We've actually seen this sequence a couple times already. How about C? How do I get from 200 to 20? We're dividing by 10. Since our growth factor always needs to be what we're multiplying by, I could write a growth factor of 1 over 10. So divided by 10 would be the same thing as multiplying by 1 over 10. Or if you like a decimal better, 0.1 would be 1/10. So 2 times 1/10 or times 0.1 would be 0.2. And then we have 0.02. Divide by another 10 and we would get 0.002. For D, I can't use the first two terms because I don't have the second term yet. So if I look at just any two adjacent terms, two terms next to each other, I see that bottom is staying the same. So whatever my growth factor is, I'm not multiplying by a fraction in the sense that I've got a new number here. This number on the bottom is going to have to be 1. So I want to figure out what am I multiplying by on top. So 9 times what would give me 27? 3. So my growth factor has to be 3 over 1 or just plain old 3. So now I can go back and fill in the missing second term. On top, 1 times 3 will give me 3 over 7. And then 27 times 3 would give me 81 over 7. And our last one for example 2, 24, 12, 6. What am I multiplying by? Multiplying by a half. Yep, 4.5, if you like the decimal better. So what comes after 6? 3. And what comes after 3? 1.5. Good. Questions for me? Not too bad? Okay. For these geometric sequences, we're always multiplying by something. And as a reminder, just like we did on our example here with the 0.75, if you have trouble figuring out what that growth factor is, you can take the second term and divide by the first term. That will give you your growth factor. Okay, any two adjacent terms, take the second one, divide by the first one, and you'll get your growth factor. So for the rest of class today, I just want you to practice working with these geometric sequences. So on page 5, you've got some practice problems here, and then you also have a Khan Academy. On page 5, you have a couple questions that are asking you to determine if you have a geometric sequence. Remember, for a geometric sequence, we are always multiplying by the same number to get the next term. Not every sequence is a geometric sequence. If we flip back to page 1, this is not a geometric sequence. I'm adding the same thing every time, not multiplying by the same thing. Example 3 is another example of something that's not geometric. I'm adding a different number each time. That's not geometric, okay? For your Khan Academy, you do have a geometric sequence each time it's asking you to find that next term. But again, for page 5, some of these may not be geometric. So it says, is this pattern geometric? You would have to decide based on how you get to the next term.